An evaporative cooler is a device that cools air through the evaporation of water. Evaporative cooling differs from typical air conditioning systems which use vapor compression or absorption refrigeration cycles. Evaporative cooling works by employing water's large enthalpy of vaporization. The temperature of dry air can be dropped significantly through the phase transition of liquid water to water vapor, which can cool air using much less energy than refrigeration. In extremely dry climates, evaporative cooling of air has the added benefit of conditioning the air with more moisture for the comfort of building occupants. Air washers and wet cooling towers use the same principles as evaporative coolers but are designed for purposes other than directly cooling the air inside a building. For example, an evaporative cooler may be designed to cool the coils of a large air conditioning or refrigeration system to increase its efficiency. History. Civilizations throughout the ages have found ingenious ways to combat the heat in their region. An earlier form of air cooling, the wind catcher, was used in ancient Egypt and Persia thousands of years ago in the form of wind shafts on the roof, which caught the wind, passed it over subterranean water in a canet and discharged the cooled air into the building. Nowadays Iranians have changed the wind catcher into an evaporative cooler and use it widely. The evaporative cooler was the subject of numerous U.S. patents in the 20th century. Many of these, starting in 1906, suggested or assumed the use of excelsior pads as the elements to bring a large volume of water in contact with moving air to allow evaporation to occur. A typical design, as shown in a 1945 patent, includes a water reservoir, a pump to circulate water over the excelsior pads and a squirrel cage fan to draw air through the pads and into the house. This design and this material remain dominant in evaporative coolers in the American Southwest, where they are also used to increase humidity. In the United States, the use of the term swamp cooler may be due to the odor of algae produced by early units. Evaporative cooling was in vogue for aircraft engines in the 1930s, for example with the Beardmore Tornado airship engine. Here the system was used to reduce, or eliminate completely, the radiator which would otherwise create considerable drag. In these systems the water in the engine was kept under pressure with pumps, allowing it to heat to temperatures above 100 degrees Celsius, as the actual boiling point is a function of the pressure. The superheated water was then sprayed through a nozzle into an open tube, where it flashed into steam, releasing its heat. The tubes could be placed under the skin of the aircraft, resulting in a zero-drag cooling system. However, these systems also had serious disadvantages. Since the amount of tubing needed to cool the water was large, the cooling system covered a significant portion of the plane even though it was hidden. This added complexity and reliability issues. In addition, this large size meant it was very easy for it to be hit by enemy fire, and practically impossible to armor. British and US developers used ethylene glycol instead, cooling the liquid in radiators. The Germans instead used streamlining and positioning of traditional radiators. Even the method's most ardent supporters, Heinkel's Gar 1/4 Enthalpy brothers, eventually gave up on it in 1940. Externally mounted evaporative cooling devices were used in some automobiles to cool interior air often as aftermarket accessories until modern vapor compression air conditioning became widely available. Physical principles. Evaporative coolers lower the temperature of air using the principle of evaporative cooling, unlike typical air conditioning systems which use vapor compression refrigeration or absorption refrigerator. Evaporative cooling is the addition of water vapor into air, which causes a lowering of the temperature of the air. The energy needed to evaporate the water is taken from the air in the form of sensible heat, which affects the temperature of the air, and converted into latent heat, the energy present in the water vapor component of the air, whilst the air remains at a constant enthalpy value. This conversion of sensible heat to latent heat is known as an adiabatic process because it occurs at a constant enthalpy value. Evaporative cooling therefore causes a drop in the temperature of air proportional to the sensible heat drop and an increase in humidity proportional to the latent heat gain. Evaporative cooling can be visualized using a psychrometric chart by finding the initial air condition and moving along a line of constant enthalpy toward a state of high humidity. A simple example of natural evaporative cooling is perspiration, or sweat, secreted by the body, evaporation of which cools the body. The amount of heat transfer depends on the evaporation rate, however for each kilogram of water vaporized 2,257 kJ of energy are transferred. The evaporation rate depends on the temperature and humidity of the air, which is why sweat accumulates more on hot, humid days, as it does not evaporate fast enough. Vapor compression refrigeration uses evaporative cooling, but the evaporated vapor is within a sealed system, and is then compressed ready to evaporate again, using energy to do so. A simple evaporative cooler's water is evaporated into the environment, and not recovered. In an interior space cooling unit, the evaporated water is introduced in the space along with the now cooled air. In an evaporative tower, the evaporated water is carried off in the airflow exhaust. Other types of phase change cooling, a closely related process, sublimation cooling differs from evaporative cooling in that a phase transition from solid to vapor, rather than liquid to vapor occurs. Sublimation cooling has been observed to operate on a planetary scale on the planetoid Pluto, where it has been called an anti-greenhouse effect. Another application of a phase change to cooling is the self-refrigerating beverage can. A separate compartment inside the can contains a desiccant and a liquid. Just before drinking, a tab is pulled so that the desiccant comes into contact with the liquid and dissolves. As it does so, it absorbs an amount of heat energy called the latent heat of fusion. Evaporative cooling works with the phase change of liquid into vapor and the latent heat of vaporization, but the self-cooling can uses a change from solid to liquid, and the latent heat of fusion to achieve the same result. Applications: before the advent of refrigeration, evaporative cooling was used for millennia. A porous earthenware vessel will cool water by evaporation through its walls. Frescoes from about 2500 BC show slaves fanning jars of water to cool rooms. A vessel could also be placed in a bowl of water, covered with a wet cloth dipping into the water, to keep milk or butter as fresh as possible. Evaporative cooling is a common form of cooling buildings for thermal comfort since it is relatively cheap and requires less energy than other forms of cooling. However, evaporative cooling is only effective when the relative humidity is on the low side, limiting its popularity to dry climates. Evaporative cooling raises the internal humidity level significantly, which desert inhabitants may appreciate as the moist air rehydrates dry skin and sinuses. Exhaust ducts and/or open windows must be used at all times to allow the cooled humidified air to continually escape the home or air-conditioned area. The evaporative system cannot function without exhausting the continuous supply of cooled air to the outside. Depending on the placement of a single cooled air inlet, along with the layout of the house passages, related doors and room windows, the system can be used most effectively to direct the cooled air to the required areas. A well-designed layout can very effectively scavenge and expel the hot air from desired areas without the need for an above-ceiling ducted venting system. Continuous airflow is essential, so the exhaust windows or vents must not restrict the volume and passage of air being introduced by the evaporative cooling machine. One must also be mindful of the outside wind direction, as for example a strong hot southerly wind will slow or restrict the exhausted air from a south-facing window. It is always best to have the downwind windows open, while the upwind windows are closed. Evaporative cooling is especially well suited for climates where the air is hot and humidity is low. In the United States, the western mountain states are good locations, with evaporative coolers prevalent in cities like Denver, Salt Lake City, Albuquerque, El Paso, Tucson, and Fresno. Evaporative air conditioning is also popular and well suited to the southern part of Australia. In dry, arid climates, the installation and operating cost of an evaporative cooler can be much lower than that of refrigerative air conditioning, often by 80% or so. However, evaporative cooling and vapor compression air conditioning are sometimes used in combination to yield optimal cooling results. Some evaporative coolers may also serve as humidifiers in the heating season. In locations with moderate humidity, there are many cost-effective uses for evaporative cooling, in addition to their widespread use in dry climates. For example, industrial plants, commercial kitchens, laundries, dry cleaners, greenhouses, Spot cooling and confinement farming often employ evaporative cooling. In highly humid climates, evaporative cooling may have little thermal comfort benefit beyond the increased ventilation and air movement it provides. Other examples: trees transpire large amounts of water through pores in their leaves called stomata, and through this process of evaporative cooling, forests interact with climate at local and global scales. Evaporative cooling is commonly used in cryogenic applications. The vapor above a reservoir of cryogenic liquid is pumped away, and the liquid continuously evaporates as long as the liquid's vapor pressure is significant. Evaporative cooling of ordinary helium forms a 1 K pot, which can cool to at least 1.2 K. Evaporative cooling of helium-3 can provide temperatures below 300 mK. These techniques can be used to make cryocoolers, or as components of lower temperature cryostats such as dilution refrigerators. As the temperature decreases, the vapor pressure of the liquid also falls, and cooling becomes less effective. This sets a lower limit to the temperature attainable with a given liquid. Evaporative cooling is also the last cooling step in order to reach the ultra-low temperatures required for Bose-Einstein condensation. Here, so-called forced evaporative cooling is used to selectively remove high-energetic atoms from an atom cloud until the remaining cloud is cooled below the BEC transition temperature. For a cloud of 1 million alkali atoms, this temperature is about 1¼ K. Although robotic spacecraft use thermal radiation almost exclusively, many manned spacecraft have short missions that permit open-cycle evaporative cooling. Examples include the Space Shuttle, the Apollo Command Service Module, Lunar Module and Portable Life Support System. The Apollo CSM and the Space Shuttle also had radiators, and the shuttle could evaporate ammonia as well as water. The Apollo spacecraft used sublimators, compact and largely passive devices that dump waste heat in water vapor that is vented to space. When liquid water is exposed to vacuum, it boils vigorously, carrying away enough heat to freeze the remainder to ice that covers the sublimator and automatically regulates the feedwater flow depending on the heat load. The water expended is often available in surplus from the fuel cells used by many manned spacecraft to produce electricity. However, the ice crystals from dumped urine, water etc., which are flying through space at orbital velocities, have been found to sandblast spacecraft. Evaporative cooler designs. Most designs take advantage of the fact that water has one of the highest known enthalpy of vaporization values of any common substance. Because of this, evaporative coolers use only a fraction of the energy of vapor compression or absorption air conditioning systems. Unfortunately, except in very dry climates, the single-stage cooler can increase relative humidity to a level that makes occupants uncomfortable. Indirect and two-stage evaporative coolers keep the RH lower. Direct evaporative cooling is used to lower the temperature of air by using latent heat of evaporation, changing liquid water to water vapor. In this process, the energy in the air does not change. Warm dry air is changed to cool moist air. The heat of the outside air is used to evaporate water. The RH increases to 70 to 90%, which reduces the cooling effect of human perspiration. The moist air has to be continually released to outside or else the air becomes saturated and evaporation stops. Indirect evaporative cooling is similar to direct evaporative cooling but uses some type of heat exchanger. The cooled moist air never comes in direct contact with the conditioned air. The moist air stream is released outside or used to cool other external devices such as solar cells, which are more efficient if kept cool. One indirect cooler manufacturer uses the so-called Morisot-Senko cycle, which employs an iterative heat exchanger that can reduce the temperature to below the wet bulb temperature. While no moisture is added to the incoming air, the relative humidity does rise a little according to the temperature RH formula. Still, the relatively dry air resulting from indirect evaporative cooling allows inhabitants' perspiration to evaporate more easily, increasing the relative effectiveness of this technique. Two-stage evaporative cooling, or indirect direct. In the first stage of a two-stage cooler, warm air is pre-cooled indirectly without adding humidity. In the direct stage, the pre-cooled air passes through a water-soaked pad and picks up humidity as it cools. Since the air supply is pre-cooled in the first stage, less humidity is transferred in the direct stage, to reach the desired cooling temperatures. The result, according to manufacturers, is cooler air with a RH between 50 to 70%, depending on the climate, compared to a traditional system that produces about 70–80% relative humidity in the conditioned air. Hybrid. Direct or indirect cooling has been combined with vapor compression or absorption air conditioning to increase the overall efficiency and/or to reduce the temperature below the wet bulb limit. Materials. Traditionally, evaporative cooler pads consist of excelsior inside a containment net, but more modern materials, such as some plastics and melamine paper, are entering use as cooler pad media. Wood absorbs some of the water and has a larger surface area which allows the wood fibers to cool passing air to a lower temperature than some synthetic materials, but natural fibers also can pose a problem with harboring or supporting mildew growth. Typical installations. Typically, residential and industrial evaporative coolers use direct evaporation, and can be described as an enclosed metal or plastic box with vented sides. Air is moved by a centrifugal fan or blower and a water pump is used to wet the evaporative cooling pads. The cooling units can be mounted on the roof, or exterior walls or windows of buildings. To cool, the fan draws ambient air through vents on the unit sides and through the damp pads. Heat in the air evaporates water from the pads which are constantly re-dampened to continue the cooling process. Then cooled, moist air is delivered into the building via a vent in the roof or wall. Because the cooling air originates outside the building, one or more large vents must exist to allow air to move from inside to outside. Air should only be allowed to pass once through the system, or the cooling effect will decrease. This is due to the air reaching the saturation point. Often 15 or so air changes per hour occur in spaces served by evaporative coolers, a relatively high rate of air exchange. Evaporative cooling towers. Cooling towers are structures for cooling water or other heat transfer media to near ambient wet bulb temperature. Wet cooling towers operate on the evaporative cooling principle, but are optimized to cool the water rather than the air. Cooling towers can often be found on large buildings or on industrial sites. They transfer heat to the environment from chillers, industrial processes, or the Rankine power cycle, for example. Misting systems. Misting systems work by forcing water via a high-pressure pump and tubing through a brass and stainless steel mist nozzle that has an orifice of about 5 micrometers, thereby producing a microfine mist. The water droplets that create the mist are so small that they instantly flash evaporate. Flash evaporation can reduce the surrounding air temperature by as much as 35°F in just seconds. For patio systems, it is ideal to mount the mist line approximately 8 to 10 feet above the ground for optimum cooling. Misting is used for applications such as flower beds, pets, livestock, kennels, insect control, odor control, zoos, veterinary clinics, cooling of produce, and greenhouses. Misting fans. A misting fan is similar to a humidifier. A fan blows a fine mist of water into the air. If the air is not too humid, the water evaporates, absorbing heat from the air, allowing the misting fan to also work as an air cooler. A misting fan may be used outdoors, especially in a dry climate. Small portable battery-powered misting fans, consisting of an electric fan and a hand-operated water spray pump, are sold as novelty items. Their effectiveness in everyday use is unclear. Performance. Understanding evaporative cooling performance requires an understanding of psychrometrics. Evaporative cooling performance is variable due to changes in external temperature and humidity level. A residential cooler should be able to cool air to within 3–4 degrees Celsius of the corresponding wet bulb temperature. It is simple to predict cooler performance from standard weather report information. Because weather reports usually contain the dew point and relative humidity, but not the wet bulb temperature, a psychrometric chart or a simple computer program must be used to compute the wet bulb temperature. Once the wet bulb temperature and the dry bulb temperature are identified, the cooling performance or leaving air temperature of the cooler may be determined. TLA equals TdB/XE. TLA equals leaving air temp, TDB equals dry bulb temp, TWB equals wet bulb temp, E equals efficiency of the evaporative media. Evaporative media efficiency usually runs between 80% and 90%, and the evaporation efficiency drops very little over time. Typical Aspen pads used in residential evaporative coolers offer around 85% efficiency, while Seldeck type of evaporative media offer efficiencies of greater than 90% depending on air velocity. The Seldeck media is more often used in large commercial and industrial installations. As an example, in Las Vegas, Nevada, with a typical summer design day of 108°F dB/66°F WB or about 8% relative humidity, the leaving air temperature of a residential cooler would be, TLA equals 108°Euro x 85% efficiency, TLA equals 72.3°F. However, either of two methods can be used to estimate performance. Use a psychrometric chart to calculate wet bulb temperature, and then add 5°F as described above. Use a rule of thumb which estimates that the wet bulb temperature is approximately equal to the ambient temperature, minus 1/3 of the difference between the ambient temperature and the dew point. As before, add 5°F as described above. Some examples clarify this relationship. At 32 degrees and 15% relative humidity, air may be cooled to nearly 16 degrees. The dew point for these conditions is 2 degrees. At 32 degrees and 50% relative humidity, air may be cooled to about 24 degrees. The dew point for these conditions is 20 degrees. At 40 degrees and 15% relative humidity, air may be cooled to nearly 21 degrees. The dew point for these conditions is 8 degrees. Cooling examples extracted from the June 25, 2000 University of Idaho publication, HomeWise. Because evaporative coolers perform best in dry conditions, they are widely used and most effective in arid, desert regions such as the southwestern USA and northern Mexico. The same equation indicates why evaporative coolers are of limited use in highly humid environments. For example, a hot August day in Tokyo may be 30 degrees, 85% relative humidity, 1005 hectopascals pressure. This gives dew point 27.2 degrees and wet bulb temperature 27.88 degrees. According to the formula above, at 85% efficiency air may be cooled only down to 28.2 degrees, which makes it quite impractical. Comparison to air conditioning. Comparison of evaporative cooling to phase change air conditioning. Advantages: less expensive to install. Estimated cost for installation is about half that of central refrigerated air conditioning. Less expensive to operate. Estimated cost of operation is 1/8 that of refrigerated air. Power consumption is limited to the fan and water pump. Because the water vapor is not recycled, there is no compressor that consumes most of the power in closed-cycle refrigeration. The refrigerant is water. No special refrigerants, such as ammonia, sulfur dioxide or CFCs, are used that could be toxic, expensive to replace, contribute to ozone depletion and/or be subject to stringent licensing and environmental regulations. Ease of maintenance. The only two mechanical parts in most basic evaporative coolers are the fan motor and the water pump, both of which can be repaired at low cost and often by a mechanically inclined homeowner. Ventilation. Air. The constant and high volumetric flow rate of air through the building reduces the age of air in the building dramatically. Evaporative cooling increases humidity. In dry climates, this may improve comfort and decrease static electricity problems. The pad itself acts as a rather effective air filter when properly maintained. It is capable of removing a variety of contaminants in air, including urban ozone caused by pollution, regardless of very dry weather. Refrigeration-based cooling systems lose this ability whenever there is not enough humidity in the air to keep the evaporator wet while providing a constant trickle of condensate that washes out dissolved impurities removed from the air. Disadvantages: performance. High dew point conditions decrease the cooling capability of the evaporative cooler. No dehumidification. Traditional air conditioners remove moisture from the air, except in very dry locations where recirculation can lead to a buildup of humidity. Evaporative cooling adds moisture, and in humid climates, dryness may improve thermal comfort at higher temperatures. Comfort. The air supplied by the evaporative cooler is typically 80–90% relative humidity. Very humid air reduces the evaporation rate of moisture from the skin, nose, lungs, and eyes. High humidity in air accelerates corrosion, particularly in the presence of dust. This can considerably shorten the life of electronic and other equipment. High humidity in air may cause condensation of water. This can be a problem for some situations. Water. Evaporative coolers require a constant supply of water to wet the pads. Water high in mineral content will leave mineral deposits on the pads and interior of the cooler. Depending on the type and concentration of minerals, possible safety hazards during the replacement and waste removal of the pads could be present. Bleed-off and refill systems may reduce this problem. The water supply line may need protection against freeze bursting during off-season, winter temperatures. The cooler itself needs to be drained too, as well as cleaned periodically and the pads replaced. Mosquitoes. An evaporative cooler is a common place for mosquito breeding. Various authorities consider a poorly maintained cooler to be a big threat to public health. Miscellaneous. Evaporative cooling towers are the most common sources of Legionella and Legionnaire's disease. Odors and other outdoor contaminants may be blown into the building unless sufficient filtering is in place. Mold and bacteria may be dispersed into interior air from poorly maintained or defective systems, causing sick building syndrome. Asthma patients may need to avoid poorly maintained evaporatively cooled environments. A sacrificial anode may be required to prevent excessive evaporative cooler corrosion. Wood wall of dry cooler pads can catch fire even by small sparks. See also, architectural engineering, building engineering, car cooler, cooling tower, dehumidifier, humidifier, HVAC, pot-in-pot refrigerator. References. External links. Holiday, April. A swamp cooler cools air by evaporation. WonderQuest Weekly Q&A Science Column. usatoday.com. Retrieved July 14, 2006. PathTech Inventory, 2-stage evaporative cooler, PathTech Inventory, evaporative cooling simulation, Colorado Indirect Evaporative Cooling. Innovative evaporative and thermally activated technologies improve air conditioning, evaporative cooling in aircraft, explained in 1934 Flight, Dengue and Coolers.